Great. Hi, everybody. This is Jacob. We're going to get started now. Um, Thank you so much for joining us today to talk about Kubernetes and load balancing in Kubernetes. My name is Jacob. I'm the Director of Solution Engineering and at HA Proxy Technologies, and I would call myself a Kubernetes enthusiast. But I'm joined with Dario here today, who's a senior software engineer at HA Proxy and is a Kubernetes expert. Dario, do you want to quickly say hi and maybe talk a little bit about your experience with Kubernetes?
Yeah, thank you so much, Jacob. So my name is Dario Tranchitella. I'm from Italy and I work for HProC Technologies. And my main involvement is about extending the Kubernetes functionalities for Fusion, Data Plane API, and the Ingress controller. And today we're going to talk about service discovery and load balancing for Kubernetes. Thanks, Jacob.
Awesome. So just a general webinar information. There's a questions panel that you can use to ask questions at any time. If I see it pop up, I'm going to try to answer the questions as they go, but we're also going to have some Q&A at the end. And then we're going to send you a recording a few days after the webinar so you can review it later. What I want to do today is I want to talk about a few topics. First of all, we should introduce HA Proxy, just kind of talk about what HA Proxy is, who HA Proxy Technologies is, so you have kind of an idea. We're going to talk about what I would call the problems, and I'm not going to say really problems, but what are the kind of difficulties with doing load balancing in Kubernetes. We're going to use that to introduce Fusion control plane, and specifically version 1.2 that we just released that kind of enables a lot of this functionality we're going to talk about. We're going to talk about a specific 3 requirements that I think exist for load balancing in Kubernetes. And because this is a fairly technical session, we're going to do a demo today. So I'm going to demo, terminal. We're going to do a lot of kubectl and some HA proxy configuration as well. So just as an introduction, we often say that HA Proxy is the world's fastest and most widely used software load balancer. And when I say kind of this big statement, I want to also use it to kind of qualify the statement, right? Like how fast? Well, we've done benchmarks with over 2 million HTTP requests, and this is actually TLS requests on a single machine in AWS and Graviton. So that's how fast HA Proxy can be. And it's very often used in requirements where it needs to be fast and have very low latency. And how widely used? We're powering the uptime of many leading companies that you might recognize here. And maybe we can talk about some use cases later that companies use, whether that's in Kubernetes or not. But I also want to introduce HA Proxy Fusion control plane. This is an important part of today's webinar. We released the control plane last year, and what the Fusion control plane does is it basically centralizes the management of all of your HA proxy instances, your fleet of instances, to make sure that it's simple to configure it and scale. And this is key here because when we're talking about Kubernetes, we might not be talking about one HA proxy instance. We might be talking about, if we're in multiple clusters, dozens of pods that might be running through your Kubernetes clusters. And it's important to be able to control and configure all of them at the same time. So when we're going to be talking about a lot of functionality today, we're going to be showing it in context of the control plane that enables a lot of this functionality. So what's the issue with Kubernetes load balancing? And I want to use this to kind of as an introduction to some of the problems we've observed from our customers. It's going to be 3 issues, ultimately. You're going to see that. I'm going to talk about one of them, and then Dario is going to talk about the others. And we're going to review those issues, and then I'm going to show you a demo of how we're going to solve some of them. So ultimately, I think that the first problem is that by nature, Kubernetes infrastructure is transitional, right? You might have pods that can be there 1 second, not the next, by crashing or scaling up in multiple Kubernetes clusters. So you don't necessarily know what infrastructure is running in your Kubernetes apps at any time, right? So it's hard typically to configure load balancing for that because you might not know what the infrastructure is. And some tools like Ingress controllers have solved that in the past, but there are still some issues right with that. I kind of joke that external load balancing outside the public cloud is NP hard, right? Because when we talk about load balancing in public cloud, it's actually quite easy to a degree. It kind of just works when you're in AWS and Azure. But when you're on premise, that might not necessarily be the case. And then multi-cluster routing is kind of the latest need. I attended the KubeCon in Chicago. I think at this point it was like a month ago. I don't even remember. And it was like the topic of the week. Everybody talked about multi-cluster routing, whether to provide like multi-region failover, AB or blue-green load balancing and things like that. So that's like a latest need that a lot of people talk about, and we're gonna talk about that in detail. Now in detail, transitional infrastructure, right? Like applications are in pods, we know that, and pods are transitional, so you can have any number of them. It scales, that's good, but at the same time, that's hard because while you could point your traffic to like a service IP, you're losing any advanced routing, right? So people often use like an ingress controller to, for example, route traffic to your pods, but then you might be losing additional functionality, or you have advanced TCP traffic that's not easy to route using ingress controllers. So irrespective, and by the way, this is irrespective of public cloud, on-premise, or anything else, kind of I define this as a requirement that we must have some kind of a process that will perform service discovery on Kubernetes and automatically update your backends from all of the pods, right? And we solve it using the Fusion control plane, and specifically the functionality that actually Dario developed in our version 1.2, which we call service discovery, right? When you might have HA proxy that is inside the Kubernetes cluster or outside, that does not necessarily matter, but you have the control plane that's actually aware of the Kubernetes infrastructure, and it's performing service discovery and automatically updating the configuration of your HA proxy for load balancing based on changes in the services or the applications inside Kubernetes. This is a little different from ingress controller because it supports TCP traffic as well. And I'm aware that ingress controller might support TCP traffic as well, but I would call this as like a TCP traffic as a first-class citizen in a sense, because it's a true real HA proxy instance that I might configure in a mode TCP, bind it to any IP address. And on top of that, and this is important for some of our bigger customers, it supports kind of all of the security features that you might need from a load balancer, whether that's global rate limiting, bot management, web application firewall. It's a standard HA proxy instance, just like you're used outside of Kubernetes. The only difference is that the backend servers are now automatically configured from the service discovery using the control plane. The second problem is, and this is kind of part of the topic of this webinar, is on-premises load balancing, right? It's actually really easy in the public cloud. You might create like a load balancer service type, right? You create like a service YAML file, you give it a type load balancer, and you apply that. And in the public cloud, seamlessly, without you even kind of knowing, if we're talking about AWS, it automatically spins up an ELB for you. It assigns a unique host name and IP address to you, and it reports it back on the service type. So later on, when you do kubectl get services, you will see a host name for your service, and it just automatically works. On premises, that's not necessarily possible. There are solutions like MetalLB, but that has problems. There are solutions like just doing like an ingress IP address, right? But that's a single IP address for all of your services. You might not have kind of separation of the host names or IP addresses and many other problems. So there are definitely problems with on-premises load balancing. And my requirements to that is kind of saying like external load balance on premises must be as easy as in public clouds. So what does that look like? Like I imagine that, you know, we might have some kind of a layer, which we call, again, Fusion control plane, that first of all manages what I call an IPAN block, right? And so when you're in public cloud and you get an IP address assigned, it's probably going to be from a block of IP addresses that AWS said that are available to this. In the same sense, we can define a block of IP addresses that we call like an IPAM block that are available to be assigned. And then having the control plane automatically pick up the load balancer service object, just like in a public cloud from your Kubernetes cluster, and automatically pick an IP address and assign it to HA proxy. So imagine like a situation where, first of all, in step one, I create the IPAM definition. I'm not doing this as a user. I would be doing this like as an administrator of the cluster, right? So you might be familiar with the syntax, right? I'm just going to say, hey, this is an IPAM definition, and these are the IP addresses. This is the block of IP addresses that are available to me when I'm creating load balancers. And then in a step two, and now as a user, so not as an administrator, so as a user, I say, look, I want to have a load balancer type for my MySQL, right? I have some kind of an application here. So I'm just going to create a standard YAML file for a service of a type load balancer. Those are the two steps. And now what happens? In a public cloud, I get an ELB, I get it reported back. I know what my host name is. I know what my IP address is, right? And we want it as easy as that. So what happens is in Kubernetes, we're now going to have the service of the type load balancer, but it's going to have a status, and the ingress IP that was actually assigned from the IPAM block is automatically going to be there. So if you do kubectl get services, you will see an external IP there reported. And on the other side, automatically in HA proxy, I'm going to get a front end with a bind. It's going to be bound to that specific IP address. And it's going to be routing my traffic to a backend with all of the servers. And the servers will be the pods or the nodes that could be actually chosen by you of that specific service that we're actually load balancing. Just like in a public cloud. This is how easy it should be. So the next is really multi-cluster routing. So Dario, do you want to talk about that a little bit?
Yeah, of course. Also because I got a strong background about multi-cluster routing, because prior being a software engineer, I was also a site reliability engineer for a company that was doing Kubernetes on-prem. So we were running everything on-prem. So we were managing our network. And of course, we were running multi-clusters. I'm saying of course, because keep in mind that back in the day, having just one cluster was really cumbersome. And now, thanks to a plethora of tools and solutions out there, you can manage a fleet of clusters. So it's pretty common having more than one cluster. And reasons behind that are multiple, I'd say, and we are going to go step by step on the available use cases. But keep in mind that it's about high availability, or rather what you would like to do is to perform an A/B testing of the applications, or rather an A/B test also for the Kubernetes versions. So with that said, keep in mind that with the Fusion integration, essentially we are supporting multiple use cases. And the first one is something that is really interesting, although it's pretty basic, I would say. So let's say I have multiple clusters and I would like to balance my network traffic across multiple clusters. The reason here are multiple, I'd say. I could have one regional cluster, or maybe one cluster in an availability zone and the second cluster in another availability zone. So I have the same version of the application across two different sites. And essentially with HA proxy and the Fusion control plane, I can balance my traffic across the two clusters. And keep in mind that here we can have the HA proxy that is set in an active-active mode, or rather active-passive mode, according to your needs. It's a feature offered by Happy HA proxy Enterprise Edition, thanks to the GPE, so the Global Profile Engine. So essentially, this is the basic concept of multi-cluster routing. Please, next slide. And as we were talking about, the AB or the blue-green is something really interesting, because what I need to do is to have this HA proxy that is going to be my entry point. And then I have my clusters. So they could be 2, 3, 4, it doesn't matter, because with Fusion Control Plane, we can check multiple Kubernetes clusters at the same time. We are calling them as Kubernetes links. And essentially what I can do is to perform this switch of the traffic, so mimicking a sort of A/B testing, or rather what I can do is to create a new cluster. I deploy all the applications in the new cluster, approaching the immutable infrastructure approach that is pretty popular across the DevOps and site reliability engineers. And once the new cluster is ready, I route the traffic to the new cluster, and then here we come. So essentially, I have a no downtime deployment, and the traffic is still flowing. And eventually, maybe what I can do is to delete the old cluster, or rather perform a switch over to the previous version. It doesn't matter, essentially. Next slide, please.
I think that, Dario, this also reminds me of, and maybe this is the previous requirement and this one at the same time, like you always need levels of high availability, right? So if you run in one cluster, that's kind of, even if it has multiple nodes, it's a single point of failure to a degree, right? So having kind of a second cluster is almost necessary for high availability, especially if you run in multiple availability zones.
I couldn't agree more. Yeah, you're totally right. Thanks.
Yeah.
And also, this is really interesting because this is one of the most demanding feature, and essentially it's multi-region clusters. So as we were speaking about, with multi-cluster, essentially you can implement a lot of use cases. And this is the most interesting because everybody would like to have a global and resilient infrastructure, and Kubernetes can help there. But of course, you cannot stretch the Kubernetes clusters across multiple regions because there are some challenges. I'm talking about the networking, the storage, and so on and so forth. So it's pretty common having multiple Kubernetes clusters across all the regions. So in this use case, you can see here that we have the first cluster that is based on US East 1, and then a second cluster that is based on US West 2. And essentially here it's the same approach that we saw before, because essentially keep in mind that Fusion doesn't need to run in a Kubernetes cluster. So Fusion is our control plane, and thanks to the data plane API integration, what we can do is to track the changes and apply the changes to a fleet of HAProxy instances. So with that said, what I can do is to ship my application, well, my configuration to the HAProxy instances. And then what I can do is to implement the global load balancer solution that HAProxy Enterprise Edition is offering, or rather I can play with DNS, I can announce my IPs. So essentially we are solving, thanks to the Kubernetes service discovery integration in Fusion, the pain of multi-region failover. So starting from there, if the first site is going down, we can detect that easily, and we can route the traffic to the new site that is still up and running.
Yeah, and what I would mention here, Dario, is that while kind of we talked a little bit about external load balancing for on-premise, these use cases are not limited to on-premise, right? US East 1 is probably some kind of a availability zone in a public cloud. So some of the customers that are using this with us are actually in the public cloud. So that's not necessarily limited to on-premise, right?
Yeah, absolutely. Also keep in mind that we were just referring to the most popular cloud service providers, but keep in mind that also there are some providers out there that are not offering a load balancer as a service solution. So with that said, with Fusion Control Plane, what you can do is to overcome these limitations and essentially provide load balancer as a service to your developers, to your applications. And essentially keep in mind that also today, the rise of platform engineering, something really interesting, is getting traction. And also how we design our CRDs, that are the customer resource definitions that you're using to orchestrate the Fusion instances directly from Kubernetes, are well defined. So we have a platform administrator level where you're defining the IPs thanks to the IPAM definition. And then the developers, they just need to apply their service objects, which are service of type load balancer, and essentially everything is running behind the curtains. So essentially the developers are going to get their IPs and they are totally hidden by the complexity because Fusion Control Plane is doing all its magic.
Instant magic. So with that, we probably should get to the demo of that instant magic, right? And maybe I can start with this use case. At the same time, before I go to the demo, there was a question in the active-active setup that's probably related to kind of the merging of the traffic or the blue-green deployment to a degree, because that's very similar. Can you control the percentage of requests to each cluster, or does it allow 50-50 only? And to that, I would just say that absolutely you can control the percentage because it's really a standard HA proxy instance that's then load balancing the traffic. So the way I would do it is really as simple as saying, hey, HA proxy, give me a random number from 1 to 100. And if the number is higher than X, then send the traffic here. Otherwise, send the traffic to the other cluster, right? Depending on my definition. Sometimes I would make it easier by putting that definition of the percentages in a map file. So I can actually edit it outside of the configuration, which I would personally do. But it's literally as simple as kind of saying, okay, what's the percentage and what's the random number right now that I'm going to use to send the traffic somewhere else. Cool. So let me just exit out of here and move controls a little bit. So what I would propose is that we start with that kind of very simple use case that we just talked about, right? So let me just pause my screen share and kind of load all of my windows. So what I want you to notice is I now have kind of two windows. At the top, I have the Fusion control plane. And in the middle of that, I have the HA proxy configuration. This is a standard configuration of HA proxy. Right now, there's nothing in it. On the bottom, I have my terminal, and I've defined a little bit of kind of definition of a few things. So first of all, I have the IPAM, as we talked about it before, right? So I just said, hey, I have an IPAM, and this is the range of IP addresses that are available to the external service. And I have a few services. So if I take a look, I have a few services here, right? But now I want to have an external load balancer for one of my services. So all I need to do, as you kind of said, Dario, kind of in the magic of abstracting away all of the complexity, is I'm going to define a load balancer type service, right? So this is a service of a type load balancer. And I'm saying, hey, please load balance the app TCP echo for me that's labeled that way. And externally is accept the traffic on port 8080, and while it's configurable, internally send it to the target port of 8080 right now. The only difference from the very most basic definition of a load balancer type is that I've used one annotation here, and that's this one. That's called IPAM definition, and I basically said use the internal IPAM, which you might remember is here. This is how I'm telling the system, hey, give me a load balancer type and give me an IP address from this specific internal IPAM block. So now I'm going to apply that, right? And I've just created a new service of a type load balancer. So if I take a look, I now have a new service. This is the service we just defined. But I want you to notice that right away, now it has an external IP, just like in a public cloud. So if I were in a public cloud, I would now get an IP address or host name of the ELB. But I'm actually on premise. I'm running OpenShift in this case, right? But it doesn't have to be OpenShift. It could be like any other Kubernetes or even vanilla Kubernetes. And right away, I got an external IP assigned to me, right? So just by creating the load balancer type, I got everything I needed as a user, and I abstracted all of the configuration. What I want you to notice is that I'm going to just right here, review the configuration, and suddenly there's a new configuration there in the control plane. And I have a front end that's listening on that specific IP address on that port, sending the traffic to this specific backend with these servers, right? So these servers are actually, in this case, the pods of that specific service, the application. And if those pods change, I will automatically get those pods applied and updated. So that's use case number one. Dario, if you were kind of to quickly look at this and say, like, how difficult would it be if I didn't have this? What would I have to do to achieve something similar if I didn't have?
That's nice because I was doing that. So essentially what I need to do is to target all the nodes of my Kubernetes cluster, implement a check, and I need to push the configuration using an automation like Ansible, so performing SSH. And that's not really secure, I will say, although, it's SSH. But the problem there is that it's not dynamic. So if I add a new node or remove a new node, I need every time to update the HA proxy configuration. And here instead is totally automated. So that's great.
Right. And just to recap, right, this is the external load balancer. So just by creating the load balancer type and saying, hey, use internal IPAM definition, I automatically go to an external IP address and notice that in the configuration of the load balancer, that external IP address is now bound to a public kind of front end on that specific port. So with this, we solved kind of the load balancer, external load balancer use case. Next, I want to show you a little bit about kind of the merging of the traffic and the multi-cluster routing, right? So I'm probably going to shift a little bit between kind of my terminal and some pictures to make it easier, right? Because I have a bigger configuration. But here's what I want you to notice. So in the first use case here, I want to load balance between multiple simultaneous clusters. So if you take a look in my configuration, just very quickly in terms of Kubernetes, I have two clusters. I have an east and west cluster. We probably don't want to merge traffic between east and west, but let's assume in this case that this is kind of in the same region in two different availability zones, right? So I have two clusters, and what I've defined is that I want to merge the traffic between them. I basically want to create a specific front end and back end that's going to send traffic between all of them. And what I've done is I've created a service definition, and it automatically created this backend for me. And this backend contains a lot of servers here because it actually contains the pods of that specific TCP echo service from both the clusters. Plus, and this is important, it contains some disabled servers that are actually just localhost. And this is important because when you have a lot of changes happening inside Kubernetes, these servers will allow us to make runtime changes without reloads, so without disrupting the traffic itself, right? So if any of the pods change on this specific class, on one of the clusters, then this backend will automatically be updated. The second scenario I have is maybe I want to do A/B or blue-green testing, right? So I've done the same thing. So in here, I've created a backend called East, and I have a backend called West. And again, that just relates to those specific pods from that specific cluster. What I'm going to do now is I'm actually going to go and I'm going to scale one of the clusters down. So from 4 replicas to 2 replicas. And so what's going to happen is that obviously I'm going to get different pods, right? So now I'm going to have different amount of pods for this deployment. But what's going to happen inside the control plane is that automatically, and I think it should be this one if I remember right. So let's take a look. Now, as it got scaled, those 2 servers or server pods that were there before now disappeared. So now I'm load balanced to the updated configuration of that specific service. Just in this case, we didn't delete them again. We just disabled those servers and made them localhost. That allows us to, in case they appear back or somebody scales the service up, we can actually update this configuration without reloading HA proxy, which will, well, reloading HA proxy will not ever disrupt traffic, but if there is a long-running connection, it's better for us to kind of not keep old processes of HA proxy, right? So we're going to update that automatically. The last one I have here is the multi-region failover. So in this case, I really have east and west clusters, but each one of them is aware of the other cluster. So in this case, if the traffic to cluster 1, to all of these backend pods, if cluster 1 goes down, the East Coast HA proxy, and in the end, there are more than one there, right, for high availability, will detect that and automatically send the traffic to West Coast, which means to the user that's coming to the East Coast HA proxy, the traffic keeps flowing. They don't even know that there was a disruption. They might get a little bit more additional latency because in the end, we're sending traffic across, across the globe. But in the end, they don't know that there's a disruption. The only thing we need to do is kind of prevent the loop back. So here's what I want you to notice. We're basically just doing a multi-cluster failover. And here we're saying, hey, the default backend on the East Coast is the East backend. But if there's a failover and a backup mode, then use the West Coast backend instead, right? And basically send traffic there. And I'm just including a specific header in the request to make sure that we can detect if there's a failback or failover. And the way it works is, if I'm going to go to my service discovery here, notice that I've defined a couple of service discovery, what we call providers. Those are just links to Kubernetes. The one that I want you to notice is, or all of them is, I'm just saying, hey, this is the cluster on the East Coast, and please monitor TCP echo service. This is the cluster on the West Coast, and monitor the same service. And in the end, or this is the merge one, here I have the merge cluster where I'm merging traffic between all of them. And in this case, monitor actually both of the clusters at the same time with the same service name. And we're going to automatically insert the information about both of the applications into the service itself. So I want to go back quickly because we've kind of reviewed a few things, right? So first of all, we reviewed a couple of requirements. First of all, service discovery on Kubernetes. This is a basic requirement for everything. So automatically update your load balancer configuration from Kubernetes, whatever happens in Kubernetes. Then making sure that external load balancer on premises is as easy as in public clouds. And you saw me create a load balancer type, annotating it with the IPAM block, and I automatically get the load balancer created. I get an external IP address, and at the same time, I get the HA proxy configuration created. And then we saw multiple Kubernetes clusters in both active-active, active-passive, or multi-region failover mode, where I can now choose how to route the traffic between all of the clusters. And how is this done? This is enabled by having ultimately HA Proxy Enterprise with our Fusion control plane, where HA Proxy Enterprise is the load balancer itself, but the Fusion control plane is basically the service that's performing all of the service discovery and controlling the configuration of the HA Proxy instance. And we released Fusion control plane about 14 months ago at this point, and it's included for all of our customers that are new customers and is an opt-in for existing customers. So you can use this and you can reach out to us if you want to use this functionality. So with that, thank you so much. We have also our colleague Senad here to kind of manage any Q&A. So I would like to go to Q&A. Feel free to open a question in the Q&A tab, or feel free to just even raise your hand if you'd like to be unmuted. But I'm happy to answer any questions.
Yeah, thanks, Jacob. So while we wait for more questions to come in, we had a few coming in on social media. So the first one was, why not just use Metal LB?
Dario, do you want to answer that, or do you want me to?
I'm the Kubernetes expert, and I'll try to do that. MetalB is a nice project, and it essentially allows to assign some IPs to load balancers, and it supports two-way. We have two modes. The first one is based on ARP, and the second one is based on BGP. And the latter one is great because essentially BGP is very robust. The first one instead is based on ARP. And the problem with ARP is that you need to rely on the IP tables if you're using IP tables for the load balancing. So essentially, always a single node of the cluster is going to be targeted. And furthermore, I will say that in Kubernetes, it's pretty common using a lot of open source projects that's fair, that's great. But at the same time, also keep in mind that MetaLB, if I recall correctly, it's not a production grade. It's still in beta, it's still in development. There are customers and users using that, and that's great because it's power of open source. But again, you're losing also the chance to customize the front-end configuration. So essentially, you got just per connectivity, network connectivity, and you cannot customize, as we are doing with Fusion Control Plane, the front end. Example generic, what happens if I would like to use the proxy protocol in the bind section? You cannot do that with MetalB because it's just addressing at the network level. Instead, with Fusion Control Plane and our integration, you can take full advantage of HA Proxy Enterprise Edition.
Cool, thank you, Dario. There was another question in the chat that I can read and I can show as well and you can talk about the specific RBAC, but for the Kubernetes provider authentication, can you explain the requirements? Is it based on any specific RBACs? So I can show you some of this. Let me just go right here. Here is my Kubernetes provider. And I can actually show you this one, by the way, because this is my throwaway cluster on a VPN. So I'm happy to show you the tokens, right? But you will notice here that basically, too long. Did I say cat? I did. Right. So this is basically like a traditional kubeconfig that's just base64 encoded. That's right here. Again, this is my throwaway cluster on a VPN. So happy for you to copy the tokens, but it basically relies on a service account that you can create with limited permissions. I don't know if Dario, you want to mention some of the permissions that we assign.
Yeah, of course. Keep in mind that essentially what we need to do is to get lists of all the pods that need to be targeted. And we need also to list the list capabilities for the services and our CRDs. And we have two CRDs, the IPAM definition that is cluster scoped. So it's the one that is going to be used by the cluster administrator, so the platform team. And then we have the service discovery resource definition as DRD. That is the one that can be used by the developers to start the scraping of their own services.
Yep.
Anyway, keep in mind that we are approaching a zero trust approach. So essentially, we are just granting the required RBAC.
That's right. There was another question. You described scraping Kubernetes for service targets of your backend, skipping the service IP port networking. Given that, are there restrictions or difficulties introduced with any CNI that restrict traffic, such as Scalico or Cilium, for the MTLS connection authorization? So maybe Dario, you can answer a little bit, but I will also mention here, if you look at some of these providers, we actually have the option in the provider to either use what we call host IPs or the pod IPs. So the default is host IPs, and in that case, it basically behaves just like public cloud. We're actually routing to the nodes instead of the pods. If I uncheck this and basically use pod IPs, then we're going to be routed to the pods, and then you might need some specific networking. But I don't know, Dario, if you want to add anything. There was like a restrictions of difficulties introduced with CNI for MTLS connection authorization.
Well, it's a nice question, and we should elaborate a bit more about that, but we don't have the time. And as Jacob said, essentially, it's totally transparent for us. So essentially, what you can do is to point to the host IPs. And pointing there, also keep in mind that since we are using the host IPs, you don't have any problem with network policies. So it means that essentially you can get in touch with the pods running in the Kubernetes cluster. And of course, it really depends. If you have your own application that has mutual TLS, you can upload the certificates on Fusion. So trying also to answer the question about MetalLB, with Fusion, essentially you can configure everything. So you can set the client certificates, and essentially it's more powerful, more flexible compared to other solutions.
Yep. Thank you. The next question was, is there any API that can be used from an operator to interact with a control plane? Yes, and I assume that maybe that's kind of to change the configuration of the HA proxy itself. You can kind of say it in the chat again if I'm right. If not, then I can adjust my answer. But absolutely, and there are actually two ways. First of all, the control plane is 100% API powered. So the UI you're looking at is actually just a UI on top of the API you would be using. So you can call an API to make changes to anything in the control plane. But at the same time, and I'm going to go back to terminal since this is a technical session, I'm just going to make it a little bigger right here. What I want you to notice is that I have some CRDs. So when we created that specific load balancer type, by default and kind of transparently to us, we created this service discovery resource definition CRD. And I cannot edit this one because it was created automatically, but you can actually create it yourself. And I'm just going to show you in the configuration very quickly. So if I created this one myself in advance, I can actually create configuration for HA proxy itself right here. So I can actually change the configuration of the load balancing from this resource definition without ever going to the control plane. So basically, I can have an operator and call the API for whatever I want. But if I actually wanted to just make some basic changes or like make sure that the configuration of the load balancer is specifically what I want, I can do it straight from Kubernetes. I don't actually have to create in my own operator. I just create this service discovery resource definition first before I create that load balancer type, and it will automatically pick it up.
Yeah, thanks, Jacob. And also keep in mind that everything in Fusion is built on top of API. We have also the optimistic locking, so we are preventing, changes that could be disruptive, as you have on Kubernetes, essentially with the resource version. And as Jacob said, what you can do is to create directly the resources configured according to your configuration template. So you don't need to write an API, an application that is interacting with the Fusion API and create more complexity. What we try to do is to implement a simple way to configure the HA proxy configuration according to the user experience that you face every day on Kubernetes. So using custom resource definitions.
Cool, thank you. Any other last questions, Sanat, from social?
Yeah, if you have time, there was a question that came in, and it was a more general question. Why is external LB so easy in the public cloud?
I think that ultimately it's because in the public cloud, and not every public cloud, right, but the major providers for sure, there is an underlying implementation of like an integration that you might be aware of, but might not even see, right? So every time you create a load balancer type object, they will pick it up. They will create the necessary components and just give you the host name. With this integration, we're basically bringing the same ease to on-premise. So it basically works exactly the same way, with the addition of the configuration actually can be customized as well. While in the public cloud, you just get an ELB and it's what it is, right? We had some last question. There's integration with OpenStack. I think that's a question that needs probably a little bit more detail, so I can follow up in more detail. I'm running my on-premise Kubernetes with OpenShift, so that's very close to OpenStack, right? But we've done some integrations with OpenStack as well. It will probably need a little bit more detail, so I'll follow up with you after the webinar. Awesome. Thank you so much, everybody, today for joining us. Hope you learned something valuable about Kubernetes and load balancing. Dario, thank you so much for being the expert on the phone and talking about your experience. We're going to send a recording later. And thank you so much, everybody.